Vibration analysis, signal processing, time waveform analysis, understanding signal patterns through temporal data. A simple time waveform, a more complex waveform. Where does the waveform come from? Use acceleration or velocity or displacement, the vibration signal. A simple time waveform represents vibration amplitude plotted against time, typically showing a repetitive and predictable pattern when the machine operates under steady conditions. For example, an unbalanced rotor produces a waveform resembling a sine wave, where each cycle corresponds to one shaft revolution. This simplicity allows analysts to identify basic faults such as unbalance or misalignment. The waveform provides direct insight into the machine's motion before any transformation into the frequency domain. It is particularly useful for detecting periodic forces and confirming machine speed. Unlike a spectrum, which breaks down vibration into frequency components, the time waveform shows the actual sequence of events, making it invaluable for spotting transient conditions or sudden changes in amplitude. Analysts often start with a simple waveform to establish baseline behavior and verify sensor integrity before proceeding to more complex analysis. Complex time waveforms occur when multiple vibration sources combine, resulting in patterns that are far from sinusoidal. These waveforms may include beats caused by closely spaced frequencies, amplitude modulation from gears or bearings, and random noise from turbulence or cavitation. In addition, impacts from looseness or bearing defects create sharp spikes, while harmonics and sidebands introduce irregularity. Such complexity makes interpretation challenging but also rich in diagnostic information. For instance, repetitive impacts indicate looseness or bearing faults, while modulation patterns suggest gear eccentricity or electrical issues. By analyzing the waveform, analysts can detect severity changes, identify transient events, and correlate them with machine operating conditions. This level of detail is often lost in the spectrum, emphasizing the importance of waveform analysis for comprehensive fault detection. The time waveform originates from sensors such as accelerometers, velocimeters, or proximity probes mounted on the machine. These sensors convert mechanical motion into electrical signals, which are then digitized by the data collector. The digitization process involves sampling the continuous analog signal into discrete points, creating a time-domain representation of vibration. This raw waveform is the foundation for all subsequent analysis, including fast Fourier transform, FFT. For spectrum generation. Understanding its origin is crucial because any error in sensor mounting, signal conditioning, or sampling settings can distort the waveform and lead to incorrect diagnoses. Proper sensor placement and calibration ensure that the waveform accurately reflects machine behavior, making it a reliable tool for detecting faults before they escalate. Choosing between acceleration, velocity, and displacement depends on the fault type and machine speed. Acceleration is ideal for detecting high-frequency events such as bearing defects or gear mesh impacts because it emphasizes rapid changes in motion. Velocity is the most commonly used unit for general machine condition monitoring, as it correlates well with vibration severity and fatigue damage across a broad frequency range, 2 to 2000 Hz. Displacement is preferred for low-speed machines or when monitoring shaft movement, as it highlights large, slow oscillations that could indicate misalignment or structural looseness. Analysts must understand that integrating acceleration to velocity or displacement can filter out critical high-frequency information, while using raw acceleration may obscure low-frequency trends. Therefore, selecting the correct unit ensures accurate fault detection and prevents misinterpretation of machine health. The vibration signal captured in the time waveform contains all the dynamic forces acting on the machine, including forcing frequencies, harmonics, modulation, and random noise. In its raw form, the signal provides a chronological view of machine behavior, revealing how vibration amplitude changes over time. This perspective is essential for identifying impacts, transient conditions, and modulation patterns that may not be evident in the frequency spectrum. While the spectrum excels at showing what frequencies are present, the waveform shows when and how these events occur, offering context for diagnosing root causes. Analysts often use both views together, the waveform to detect irregularities and the spectrum to pinpoint their frequency components. This combined approach ensures a thorough understanding of machine condition and supports proactive maintenance strategies.